All right, now we're going to move on to some more new material. As you know, some languages like C allow you to use pointers at a high level. Other languages don't allow pointers at a high level. I think Java and C are the most classic examples of two different philosophies about pointers. But at least you know what pointers are because you've been learning some C++ in your CS-201 and CS-202. And you know that pointers are one way to address something in memory, but it's not a high-level way, it's a low-level way because pointers actually refer to a memory address. And you also know that arrays are another common way to refer to something in memory, also trees and queues and all kinds of things. But arrays involve indexing the data item by multiplying the index by the element size. We've been doing a lot of, I sharp of 4 multiplication, if you remember, because I is the index. If you have an array of words, a word is 4 bytes. So now you know how many bytes you are offset from the base of the array. But then you have to add that to the array base address, and now you've got the memory address of the item you want. That's one way. Calculate it from the base address and the index using a multiplication, and then after you got that, plus array base. Okay? So you got two operations. You got to multiply and you got to add, and now you know the memory address of, let's call it A sub I. So the thing you want, you finally calculated it. And with pointers, they correspond directly to a memory address. So you can avoid the whole indexing business if you use pointers. So that's the unsos. Does everybody know that information already? I hope. But it's good to review it. So pointers point directly to the thing you want. Arrays use a base address of the beginning of the thing you want. And the item you want, you have to calculate it by this method. Now, let's say that our task is a very simple task. We want to clear out the values of an array and make them all to be 0. Clearing an array. Let's say that we have something like that. So the array code would look like this. Clear 1, where you're given the base address of the array and the size of the array. And you declare a local integer I. And starting at I equals 0, all the way up to the size of the array, adding 1 to I, you do the following. Let the element referred to by array I have its value set to 0, and let's just keep doing that until we're done. That's one way to clear out an array. That's called array indexing. It's very clear that the array is visible, the index is visible, and you're telling it what to do in the high-level language. The assembly code for that will look something like this. First, initialize, before you get into the loop, the value of I. I is going to be held in our T0 register, so we move 0 into T0. Everybody knows that move is not a real assembly language instruction. What do we call this kind of thing? Pseudo instruction. Yeah, and how would the assembler actually implement move? Adding to register 0 to register 0 and put the result in T0. Yeah, exactly. Okay, now we have a loop, and I want everybody to notice that the loop includes 1, 2, 3, 4, 5, 6 instructions, because this says bottom branch back to the top. Here's the top. So my loop is 6 instructions, and in the loop you can see that I'm shifting left by 2 places the value of T0. Anybody recognize what shifting left by 2 places does? It does this, doesn't it? It's a cheap way to multiply by 4. If you actually multiply by 4, it'll take the machine a lot longer than a shift. Okay? So this is a fast multiplication. So that's I times 4. And then we're adding I times 4 to the base address of the array, which is in A0. That would be this value given here, passed into the called routine, of course, as a parameter in the A registers. That's where we hand parameters. So it's handed in. We add them together. And so this value in T2 has just done this computation. The shift did this, and the add did this, and now we've got the memory address of item A sub I in T2, and we use that memory address in order to do what? Store the value of the 0 register into that address. So that's actually doing the clearing right here. And then after that, we increment our value of T0, which is our I. So we increment by 1, that's this. And then we do set less than followed by BNE. Whenever you see a set less than followed by a BNE or a set less than followed by a branch, you should understand, ding, 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 the two of them are working together in order to give us what? In order to give us what? Remember the branches? Here's the branches. Is it equal? Is it not equal? Is it greater than? Is it less than? Is it greater than or equal? Is it less than or equal? For how many of these do we have an ability to do it in a single assembly language instruction? This one, that's BEQ. This one, that's BNE. How about this group of 4? Can we do those in a single assembly language instruction? No. So we know that we're going to combine set less than with one of BEQ or BNE, and in combinations we're going to get yeah this, yeah this, yeah this, yeah that. So I'm picking out one of those. Can you look at the high-level code and tell me which one I'm implementing? Yeah, it's testing, is the value of this thing greater than size? Okay, so it's actually looking to see here, is I greater than size, or less than size, we put that into T3 and then we test on it, and we say if it is, it's time to leave, but if it isn't, if these are not equal, no, let me get this straight, yeah, if they're not equal, if this is a 1 and that's a 0, go back. If they're both equal, which means it's 0, meaning it wasn't less than, meaning it's equal or greater, we get out. But as long as it passes this test and we set this to 1, this 1 and this 0 will be not equal, we'll take the loop and go back. Okay, so that's a literal interpretation in assembly language code of this high-level code. Does anyone have any questions about it? The loop has 6 statements inside the loop. Now, it's a bottom-tested loop. It's not got a J and a middle test, so we've already gotten rid of the accessory jump instruction. But that's it. The array code gives us a loop size of 6. Good. Now that you understand that, that's pretty easy to understand. Let's come over here, and the first thing I want you to look at is we're branching back to loop 2, and loop 2 is here, and we have 1, 2, 3, 4 instructions in the loop. So this loop is going to run 50% faster than this loop. Okay? It has 4 instructions instead of 6. So right off the bat, you ought to say, well, then I better pay really close attention to understanding how to implement this because it's better. It's way better. It's better. It's way better. That's the first thing that you should see. Second thing you should say is, okay, this is a clear routine using pointers. So somehow pointer code at the high level gives me better assembly language code at the low level. I guess I better learn pointers. Even if I hate them in my C++ lesson, I guess they're important for performance. That's the point. Okay, now let's go into the pointer code. But the unsos is pointers have a significant advantage in performance. It's not just ister array, ister pointer, whatever Hoshima Gider. It's not like that. It's like this is slow and this is fast. Hello? Yeah. Okay, so now you've got to make a choice inside you. Should I therefore go back and work harder to learn those pointers, which are hard and awkward in C and C++, or should I say, bo schwer, I'm not going to write fast code the rest of my life? I'll leave the choice up to you. But that's really what it comes down to, doesn't it? All right. Now, in just a minute, I'm going to give you some good news. But let's go into this. Okay. The clear 2 accomplishes the same thing as clear 1. It says, pass me the address of an array. Tell me the size of the array. I'll have a pointer value P, which is a memory address, as you know. And for when that memory address, starting at this value, goes up to this value, incrementing it by 1 each time, please make sure that the value at that address is set to 0. Okay? So basically same thing here, but using the stars and the and sign. Yeah, it's awkward. You know, I admit. This star and this and sign make things a little more complicated. But if you can remember that one of them refers to the address and one refers to the thing at the address, it's actually not much different than this. Because that's what's also happening here. Array isn't the thing at the address. Array is the address. Okay? That's the value of the starting location, not the starting value in the array. That's a value. That's an address. Okay? All right, here we go. We're going to take our value of the starting address of the array of location 0 and put it into T0. And we're going to multiply by 4 the size of the array, which is passed in A1. So the array, which was maybe 10 elements, has now become 40. Can anybody tell me why size should be 40? Well, it is in bytes. It is in bytes. It's just not in words. So whatever the size was of this in integer words became multiplied by 4 in bytes. So now, what is this T1 going to do for us? Anybody have an idea? Why did I want to find the maximum byte size of this thing? Oh, and then go on and add it to the base address to form whatever that is. What is that thing? Yeah, that's the last memory address, or even beyond. It's one more, I guess, because we took the 0 and multiplied by. So that's actually, if you've gone there, you've gone too far. You're outside the array. It's a physical address, isn't it? Okay, so that's going to be my limit. And I bet if we look down, we'll find that in our test. T2. Oh, yeah, there it is right there. We're comparing the T0 value to that T2. All right, so that becomes a limit. We pre-compute the limit before we go into the loop. And we say, when do I stop this loop? The answer is when T0 hits T2. Okay? All right, let's go on. Now, we're ready to come into the loop. What do? We take the T0, which is the value of the, sorry, that's the wrong way to say it, the address of the first element in the array, and we say, let the value at that address be cleared to 0. If you notice, that's very similar to this line here. Just clear it to 0. And then we say, take that address and add 4 to it. What do we do here? Take that index and add 1 to it. Oh, but by the way, multiply it by 4. We're a lot smarter here. We're just saying add 4 to the value of the address. So what's it going to point to now? The next element in the array. Now I've added 4. Now it's time to do our test. Our test is going to be similar to this as well. If we're done, go out. Otherwise, go back and loop. Okay? How do we know if we're done? Because the value of the memory address, not the value of the memory address, excuse me, the memory address that we're now pointing to is tested against the maximum, which is too big, which we computed here. And if you're equal to that, you're done. You've gone out of the array. That's the finish. As long as this is less than that, we're good. Keep going. But when this becomes equal or greater than that, we're done. So we're using literally a memory address in T0. What are we using over here in T0? An index to an abstract data type. And we're converting that abstract index by multiplying by 4 and by adding to a base address inside the loop. You notice here, we did a multiplication, we did an addition outside the loop. Did it once, as opposed to every single time. And that's where the two lines came from. Look, these two are actually in here, and they're actually out here. So my loop now only consists of set it to 0, increment the loop control variable, and do the two-line test. Set it to 0, increment the loop control variable, do the two-line test. But unfortunately, I'm doing the multiplication and the addition in the loop with the index approach, and outside the loop with the pointer approach. Okay, now, do you get that? Is that something that resonates with you? Yeah, okay. I hope that shows something very significant that maybe you never saw before. There's a lot of value in going below the high-level language, down below the hood, below the surface, below the stage, and seeing what's going on at the machine level. This is the code that the compiler would generate from this. This is the code the compiler would generate from this. Now, if you took this code and you optimized it, you would say, well, you know what? Adding 1 and multiplying by 4 is silly. Let's just add 4. Uh-oh. And then that starts to look like this right here. And as you tuned it, you would first kick out the shift, and then you'd kick out the addition, and you would have turned your index code into pointer code without realizing it. In other words, you hand optimizing, or a good optimizing compiler could still start with this, go to this, and then optimize, and end up with this. So that's the good news that I promised you. I said, don't feel too bad. You can still hate pointers. You can still avoid them, because optimizing compilers have made up for your laziness and your unwillingness to work with them. In other words, you can still write this and get this, because the optimizing compilers have filled the gap. It wasn't true in the early years, but they've gotten so good now that optimizing compilers can, shall I say this, make up for bad code choices. You know, they can't make up for bad algorithm choices, but they can make up a lot for bad code choices. Oh, well then I don't even need to go to Bilkent. I can just write some sloppy stuff and the compilers will fix it all. We're not there yet. But wouldn't it be nice if someday you could talk to your computer and say, you know what, I need to compute the average of the, daily temperature in Ankara over the last 100 years. Please do that for me. And you just talk to it. You would tell what you want at a high level, and the computer will understand, write correct algorithms, optimize them, and wouldn't that be lovely? Okay, that's the holy grail of computing, is to be able to have machines that are intelligent enough to respond to us at our level without having to say, oh, I don't know if I'm going to choose index or pointers. I don't know about, it'd be great, but we're a long way from that. If you're interested in this field of having compilers do more and more of the hard work so that we can work at a higher level, not have to deal with asterisks and signs and not have to deal with indices and loop control variables, then I strongly encourage you to stay on for a master's. In fact, go for PhD, work in the area of programming language semantics. You're going to take next year a course called Programming Languages. I think it's 315 is the code. Very important course because it's about the level that current languages are at and how to move it up closer to the human level. Of course, as they move up, who's filling that greater and greater gap? The machine languages aren't moving up, so as the high-level language moves up, the compilers have greater and greater challenges in order to fill that gap. Okay, and that's why I encourage you to take the compiler course also. Programming language is required. You don't have a choice in that. It's in the must course list. Compilers is a technical elective that you can take from our department. I forget its code number. Okay? But these are interesting and very challenging problems, worthy of study, worthy of work. Okay? If you want to understand computing, this is part of understanding it. Okay, I got to move on. We've got just a half an hour left. If we compare the array and pointer versions of these two codes, we've pretty much done it, but the first thing is we reduced multiply to shifting in both codes. We call that a strength reduction, and it saves time because a faster instruction was substituted for a slower instruction. Both versions used shift left logical instead of multiply. The array version required the shift to be inside the loop, part of the index calculation that we showed here. Incrementing the pointer and multiplying it by 4 and adding it, the compiler can achieve the same effect as manual use of pointers. And I said that. You could start with this, compiler would generate this directly, then optimize it and get it over to here. It eliminates the induction variable, that was the I. It makes the program safer and clearer to not write with pointers. And so compilers can fill the gap. And optimizing compilers do these things and many, many more things. Now, we don't have time, but on the CD-ROM in the back of your book, there's a section of the chapter that's not printed. It's section 215, and it shows a lot of cool things that compilers do on the back end to optimize the code and make it faster. I hope that when I showed you the slides earlier about this stuff, and I showed that optimizations can speed things up, I hope I raised your curiosity. Well, how do they do that? What do they do to get faster and faster code? How do they get rid of instructions in order to make the thing run quicker? Well, in section 2.15, at the back of on the CD-ROM, there's answers to those questions. I wish I had more time, but I'm not able to go any deeper than that. I've just hopefully given you an idea about what compilers are capable of doing. Okay, now we come to the last part of our chapter, which is comparing some other architectures. We've looked pretty deeply at the instruction set architecture of MIPS. Now what I'd like to do in the next half hour is look not so deeply at the instruction set architecture of ARM, ARM, which is another processor of the same general category as MIPS, a RISC processor, and then look at the instruction set architecture of the Intel series, which is a very different kind of architecture. So we'll start out by talking about ARM. ARM and MIPS have a number of similarities. They are similar because they came out of the same RISC revolution of the mid-1980s, and so they have an instruction size, an address space, a data alignment which are identical, and also the input-output being memory mapped. And they're not very different even in some other things. ARM decided to go with 15 general-purpose registers, and MIPS decided to go with 31. You can see that both of them dedicated a register to a fixed value because 32 and 16 would be natural sizes. So one of them has been given away to something like a 0. I asked in the quiz today how many addressing modes there are, and in the little brief tutorial after we saw there's 2 code addressing and 3 data addressing modes. ARM has got a lot more ways to address data, 9 different data addressing modes. That's a reasonably significant difference. Okay? But otherwise, a lot of similarities. In ARM, comparing and branching is quite different than it's done in MIPS. They use condition codes, which result after an arithmetic or a logical operation. So when you do an arithmetic or logical operation, some code bits get set or cleared as a consequence of that operation. Okay, so a negative bit, a 0 bit, a carry bit, and an overflow bit are stored automatically every time there's an arithmetic or logical instruction in something called the program status word. It's just an extra register that stores these bits. And so once those bits are available, they're part of the architecture, now you can have instructions which compare and set condition codes without having to keep the result. You can actually just use those bits without changing anything in any other register in order to make a decision about branching. Okay? In fact, you can make decisions even about skipping instructions. Every instruction can be conditional. So watch this. Add conditional. What does that mean? That means if the conditions are met, do this addition, otherwise just skip right over it. Okay? Subtract conditional, or conditional, branch conditional, etc., etc. So with this, you're saying refer to those status bits and check, and if the match happens, then do it, otherwise don't do it. The top 4 bits of every word, and you'll see in the instruction formats on the next slide, are set aside for the condition value you want to test. So you say in your instruction, here's the bits I'd like to check. Please go refer to the ones that were stored from previous instructions, and if there's a match, let's do it, or if there's a match, let's don't do it. And so it allows you to avoid branching over single instructions because you can just skip them instead. There's no need to branch over this if I have the ability to just come to it but not do it. Right? So if I can just say, do I do it, yes or no? If the answer is no, it's the same as branching over it, but it avoids the branch instruction. Okay, so that saves code space and saves saves execution time. So here we go. The register-to-register mode in MIPS, as you know, looks like this: 6-bit opcode, 5-bit, 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 a constant, and then an extension to the opcode. And the data transfer mode, which is our I type, looks like this: the opcode, 2 registers, and a 16-bit constant. And the branch looks like the same: the opcode and 1 or maybe 2 registers and a 16-bit constant. And the jump looks like this: the opcode and a 26-bit constant. Those are our formats in MIPS. Now let's go back and look at them in ARM. Remember, ARM only has 16 registers, so we only need 4 bits for our registers. But I want you to notice that there's a register source 1, which is 4 bits, register source 2, which is 4 bits, and a register destination, which is 4 bits. In other words, add R1 to R2 and put it in R3. They can do that just as well as we can do that. I want you to notice that the operand is a, what does that say, 8-bit operand instead of 6, but there's a 4-bit extension, which is what I just mentioned to you, those 4 conditional bits. And if they match, we will do this. If they don't match to the ones that are stored in the status register, we won't do this. It makes the whole thing conditional. And then our 8-bit operand is supplemented by an extension, just like we supplement by an extension. So pretty similar, except for the fact that it can be made conditional, and the fact that there are 16 registers instead of 32, so there's 4 bits needed instead of 5. That's the register to register. On the data transfers, again, there's a 4-bit prefix for the condition codes. We will or we won't do this transfer conditionally on some things that are already set in the machine if there's a match. Here's our opcode. Here's our source register. Here's our base register, if you'd like to call it. Here's our displacement or offset. So we form the memory address, typically like this, remember? You know, offset value base. That would be the offset value, that would be the base. And where do we put the thing that we brought in from memory? Here. Or where do we source the thing we're sending out to memory? From here. So there's the register, that's the destination. Just like we have here. Very similar. Okay? Then the branch instructions, again, you can see there's a code for the branch, and there's a constant to say where we're going to branch to. And the only difference is there's a 4-bit prefix that says the conditions of the branch. If you match those, then do it, otherwise don't do it. Notice that the branch target can be further away in ARM Look at that. We got 24 bits. That's a long way to go if it's PC relative. Much longer way to go than our 16 bits if it's PC relative. But I'm not sure if it is because look at their jump instruction. Their jump instruction has exactly the same format as the branch instruction. Whereas for MIPS, the jump and branch formats are quite different, aren't they? Yeah. So remember, this long constant of 26 bits was for pseudo-direct. And it makes me think perhaps ARM is using pseudo-direct for both their branching and their jumping. Again, the opcode, again, a 4-bit prefix, opcode 4-bit prefix. So that 4-bit prefix exists in every single one of the ARM instruction formats. All right, any questions? Looks pretty similar, except for this 4-bit conditional field that allows you to decide are you going to do it or not do it, okay? Based upon matching these bits you're asking for with bits that are stored. In other words, you could say, if negative, the last thing that was done, then please do this jump. You could say, if the value is 0, then go ahead and do that operation. You could say, if it's less than 0, or if it's an overflow, or if it was a negative value, then please do it. Otherwise, don't do it. Or terse. If it wasn't negative, do it. If it wasn't an overflow, do it. If it wasn't equal to 0, do it. So you have those kind of options in this 4-bit code. Obviously, 4 bits allows you 16 different sets of conditions that you could choose to have as your branch condition. All right. That's the ARM. It's, again, as I said, a similar philosophy and architecture to MIPS. So a lot of what I've taught is transferable. Now what I'm about to explain is very different. Very, very different. But everybody's curious because this is the Intel/AMD processor that's inside your desktop, your laptop. This is the baby that makes the world go around. I mean, 100 million of these were sold last year, and this is the desktop portable processor world, pretty much. Okay. Oh, by the way, what about ARM? Is this a... Come back here. What about ARM? Are they just some dinky little company in England that sells a few every year?
Smartphones, portable devices.
Yeah. Yeah. Okay. Smartphones, so little portable devices, and everybody I hope knows that there are way more portable electronics sold than there are desktop and laptop PCs. So ARM sells more than Intel plus AMD put together multiplied by 10. It's more than that, okay? ARM processors and all the other embedded processors are an enormous market in cell phones and in PDAs and in, Apple, whatever their iPhones and this, that, and the other, game boxes and, all that stuff sells way more. Those are called consumer electronics. This is not considered consumer electronics yet. But embedded processors are sold to both consumer electronics and also, of course, to all kinds of appliances. So the market is much, much larger. Actually, ARM sells far more processors than Intel and AMD put together, multiplied by 10 even, more than that. Okay, so this is not a dinky little British company that nobody should ever hear about ever again. This is a major, major microprocessor manufacturer. It's just not the microprocessor that powers our desktop computers. They're aimed at a different market. Okay, now let's talk about Intel. And by consequence, Intel plus AMD, because AMD and Intel are sort of cloning each other and have to produce the same instruction set architecture, the hardware that supports the same ISA. Okay, the next 3 slides are going to talk about the evolution of the Intel processor. And it's quite a long evolution. And so the title of it is well chosen. Evolution with backward compatibility. In other words, this processor has developed, but at each stage of development, the choice was made to keep the new one where it still ran all the old code. That's called backward compatible. So it runs all the old code, but it added some new features to run new code as well. Okay, back when I was a student in 1974, I remember when the first 8-bit microprocessor came out. Intel had a version before that, which is a 4-bit microprocessor called the 4040. But the big revolution was the 8080, because with 8 bits you could actually do some useful computing. And I actually programmed some 8080 and 8088 and 8086 programs in my student days. It had an accumulator plus 3 index register pairs. An accumulator is different than a general purpose architecture. Then in 78, the 8086 came out, and that was a 16-bit extension of the original architecture, and it added a lot of new instructions, and so it became a complex instruction set computer. In 1980, floating point math was important enough that a coprocessor chip came out, which later got integrated on the same chip, but it was a separate chip called the 8087. So with the 8086 and 8087, you could do integer as well as floating point math, and they talked to each other and shared. This floating point coprocessor therefore added floating point instructions and a register stack in order to be able to do the floating point arithmetic. Then in 82, the 286 came out, which got us up to 24-bit addressing, because 16-bit addressing means you're limited to only 64 kilobytes of memory. As soon as you go to 24-bit addressing, you can go up to 16 megabytes of memory, much, much larger. And it added a memory management unit, and these are all on chip, as far as I remember. And memory got segmented. Remember, I talked about memory segments, code, operating system, data, dynamic data, static data, dynamic data, and stack. Okay, it's segmented memory, and you'll see in just a minute. And protection, so that processes didn't interfere with each other's memory areas or with the operating system's memory areas. And then in 85, the 386 came out, which was a 32-bit extension, and now it got a name. The architecture's name was IA32, which stayed for about 20 years until in the mid-2000s. Additional addressing modes, additional instructions, paged memory mapping, as well as segments. So we have both paging and segmentation as two different ways to look at memory. Then in 1989, I know this seems like ancient history to you, but it's the development of modern processors, so I hope that it's at least somewhat interesting. Pipelining, on-chip caches, floating point unit, again, more instructions were added. And competitors came out, CISC and AMD and other companies that said, we can do that too, and we'll sell you one that either runs faster or costs less. So Intel had competition starting in the late 80s. Pentium started coming out in the 90s. Superscalar, meaning able to execute more than one instruction per clock cycle. 64-bit data path internally, even though it was still a 32-bit external world. Later versions added multimedia instructions and the famous division bug. So that's pretty famous, unfortunate history for Intel. Then Pentium Pro in 95, Pentium 3 in 99, Pentium 4 in 2001. You can see that they just keep changing the architecture, adding instructions. That's not all. We move on. In 2003, AMD, instead of just saying, okay, Abi, whatever you do, we do, decided to take the lead. And AMD extended the architecture and said, we know how to add instructions and make it more complicated and do new things. So the architecture was extended to a full 64 bits, called AMD 64. And then Intel responded with EM64T, Extended Memory 64 technology, a year later, which adopted the AMD stuff and added more. So we had already SS2, and now we've got SSE3, SSE2, SSE3, there was an SSE1. So extra instructions are being added at every one of these. Here's SSE4, again, more instructions. So you're going to see in a minute a graph of number of instructions. This is a very complicated architecture with many instructions. Support for virtual machines. AMD announced SSE5. Intel didn't follow it. Instead went with advanced vector, announced in 2008. Longer SSE registers. And so the bottom line is, if Intel didn't extend the architecture but keep compatibility with the backward code, its competitors certainly would have, so they were forced to. So it's this race of extend but keep backward compatible. Don't lose any customers or they'll go to your other competition. Extend more but with backward compatibility. So in the end, what you have is processors that could be said, yeah, they're successful in the market, but they are technically very inelegant, very ugly, in fact. All right, now let's move in. That's the history and the extensions, and so it evolved. It wasn't set down and planned by a group of architectural, high-level processor engineers to design a clean architecture. Tom Terce. It kind of evolved up step by step and just kept adding more and more. So it's not going to be very pretty. Let's have a look at some of the insides. This is the basic set of registers. They initially were 16-bit. As you can see, they've been extended. That's why E, the AX register, is now extended AX. The CX is extended. The DX is extended. So these registers are general purpose registers. There's only 7 of them. And that's not very many, considering that ARM has 15 and MIPS has 31. But that wasn't, 7, they weren't even general in the beginning. They were the AX, CX, DX, BX, SP, BP, SI, and DI, indicating they had purposes, don't they? But they later became general and are extended to 32 bits. Some are still 16-bit internal registers, or were for this base architecture. A code segment pointer, which says where is the code segment. A stack segment pointer saying where is the stack in memory. Data segment 1, 2, 3, 4. Where are the data segments for my process in memory? An instruction pointer, which we call PC, program counter, or sometimes called instruction pointer. And then condition codes. I mentioned condition codes with ARM. I said that in the processor, a register keeps a set of bits that are the conditions. They show what happened in the last instructions. Intel calls them the flag register, and it's been extended to 32 bits. And the instruction pointer has been extended to 32 bits. Remember what we said? Initially, it was a 16-bit architecture. That meant your addresses were 16-bit addresses. Didn't need them. Later, they were extended to 24 and 32. So that's the set of registers. We can say not as many general-purpose registers, more special-purpose registers, extended in order to meet growth over time, and yeah, probably specialized more than MIPS, although ARM has the kind of this sort of thing. Very specialized here, as opposed to general purpose can point anywhere in memory. Now we've got this points to that segment, this points to that segment, these point to that segments. Okay, well, that's the first comment to make. Second thing is about instructions. The classic MIPS instruction looks like this. Add R1, R2, R3. We've got 2 source operands and a destination. 3 operands. But with the Intel architecture, 2 operands. So that means that one of your sources has to also be your destination. So it will look like this. The meaning is, add those 2 and put it there. Oh, you're forced to change R1. You're forced to change one of your sources every time. You're not forced to change one of your sources in MIPS when you have 3 operand. Second thing to notice is that we allow sources to be in memory. Can you notice that in this set here, one of the sources can be register or memory. The other source can be register immediate or memory. And the destination can be register or memory. So in theory, you might be going to memory 2 different times in an instruction after you fetch it. You might be going to get one of your sources, and then you'd go again to put the result back into memory. Notice that when this one's memory, we don't allow this one to also be memory. So we don't allow 3 memory references per instruction, but 2 is bad enough, let me tell you. The memory addressing modes are multiple. Remember our memory addressing mode? Base plus displacement. That's it, base plus displacement. This is, the address in memory is found in a register. The address is the base plus a displacement. The address is the base plus 2 scaled up to some power multiplied by an index, where scale is 0, 1, 2, or 3. And then the address is the base plus 2 scaled up to an index multiplied by R plus a displacement. So we've got 4 different memory addressing modes. And obviously quite a bit of complication if you're going to have exponent powers, multiplication, and addition. You're going to be calculating quite a lot to get your memory address. And doing that twice if you use this mode or this mode. So does it sound like the instructions are going to be fast to execute or slow to execute to you? Sounds like slow. A lot of complication in implementing such powerful instructions. So what have we seen here? We've seen that they have a lot of instructions, but they allow them to be complicated instructions. Okay? Complicated instructions. So that's why it's called complex instruction set computer. The instruction set is not only large, but the instructions themselves are complex. Powerful might be another way to say it. Okay, now let's look at the formats. MIPS had 3 formats. Intel's got 1, 2, 3, 4, 5, 6, and more after that. But this is just 6 of them that are shown. I'd like you to notice a couple things here. This format is 2 bytes long. This format is 5 bytes long. This format is 3 bytes long. This format is 1 byte long. This format is 5 bytes long. This format is 6 bytes long. So the length of an instruction is variable. And when you fetch it, you don't know how much more there is until you fetch and decode, and then you know how much more to go get. Does that sound like it's going to lead to fast execution or slow execution? Yeah, if I have to fetch and decode in order to know how much more to get from memory, that's not nice. All right, so now you can see that we have, for example, here's a jump. Here's the condition to do the jump. Here's the displacement. Here's a call. That's going to mean call, like our JAL. Call this place with a 32-bit offset. Here's a move. And I've got a thing called a post byte. It turns out the values in that post byte will affect how the move is interpreted, as well as 2 bits here for D and W, as well as the displacement. Here's a push. A certain register value will be pushed onto stack. Here's add, where I've got a long immediate value, excuse me, and a register that are going to be combined, and of course the result has to go into that register. I had to, whatever that was, I had to change it by adding this value to it. Here's a test instruction, which is going to test and set some of those bits. Again, the post byte and the W will compare this 42 to something. So that's some idea about the complexity. Variable length encoding, the postfix bytes specify the addressing mode. Remember, we got these 4 different memory addressing modes, so the postfix bytes tell you how to calculate the address. Prefix bytes modify the operation. Okay, that's not even shown here, but there's some prefix bytes here that tell you, are we going to be doing this repetitively? Are we locking anything before we do it? And what the length of the operands are. So we've got both prefix bytes, which aren't even shown here, that add complexity. The postfix byte, which tells you how to calculate the address. So you can imagine that this is going to be complicated to implement. The decoder and the control unit for this kind of a processor will not be simple. All right, implementing this. Okay, now it comes time to build it. You're the engineer at Intel, you're the engineer at AMD, and it's time to build the hardware to implement this instruction set architecture. Remember, ISA comes first, and then we choose how to implement. AMD has chosen some different implementation strategies than Intel, claiming to get better performance for less cost. Here's the problem. Complex instruction sets make implementation difficult and expensive. You need a team of very sophisticated engineers with very powerful tools, working hard night and day, putting in man-months, man-years of effort in order to come out with a reasonable performance when they implement, making up for the weird, ugly, large instruction set architecture that you've designed. It's kind of like trying to make up for bad code with a good compiler. We did that example earlier. Bad code can still be improved with an optimizing compiler. This is kind of like, with really good implementation, can we make up and get reasonable performance out of a very messy architecture? The hardware translates the instructions, which are complex, into simpler instructions, which Intel calls micro operations. The simple instructions at the assembly level will translate one-to-one into micro operations, but the complex instructions will translate one-to-many. So one complex instruction of the kind that we showed here will translate to many of these micro operations. Now the micro operation engine is actually similar to a RISC machine. Executes them reasonably efficiently. And because Intel has a large market share, their profit allows them to be able to do such things. Okay, so it's a weird translation back to simplicity at the low level because they didn't give it at the high level. But in the end, simpler, as you know, leads to faster. We've talked about that as a design principle. You can get comparable performance out of this to RISC because compilers tend to do something very nice for you. They tend to avoid the complex instructions, which are slow, and target the simple instructions, which run fast. So the compiler says, well, that's nice that you have all those complex instructions, but I'm not going to translate the high-level code into those because those are slow and awful. I'm going to translate into your subset of faster instructions, which are your simpler instructions. Great. That's good. So you can get good performance. The only problem is you paid for the hardware to implement all the instructions, the hundreds and hundreds that exist, and most of the transistors in the control are designed to help allow for that, even though the compiler is distinctively avoiding that. So what are you doing? You're paying money for something you're never using. Okay? It's like getting a Maserati which can go 240 miles per hour. I forget how many kilometers that is, 400 kilometers per hour, and then driving it on the city streets in Ankara. Nice car, but you can't use its capability. You got to go out to a track if you're going to use your Maserati. Got it? So you spent $250,000 on your Maserati, and you're driving it around on, Argentine Jadasi at limits, and the police are looking all over you. If you go faster than the limit, your goose is cooked. All right. So now, yeah, I'm running out of time, and you can ask a question.
United States price
Yeah.
in Turkey,
Yeah.
Maserati,
Yeah.
250 euros.
Euros, 250,000 euros. Okay, thank you. All right. I don't own one. I'm just guessing. That was just a guess. All right, it's time to finish. So let's do this last slide real quick. Powerful instructions. Some people think they lead to higher performance, but in fact, that's a fallacy. They don't. Complex instructions are hard to implement, and they can actually slow down all the instructions, including the simple ones. Compilers are good at making fast code from simple instructions. So if you feed compilers simple instructions, they generate really high performance code. And so assembly code for high performance, that's the way to get fast performance, is tune it by hand. Another fallacy. It's not true. Modern compilers are able to deal with high-level code and turn it into very high-quality, low-level code. And because of that, if you write at a low level, if you write at assembly, more lines of code, of course, will be the result, because it's not, compact and efficient, and that'll lead to more errors. So actually, both of these are wrong. It's better to write at high level and let compilers take care of you, and it's better to use simple instructions because compilers are good. So the role of the compiler was the key message of the class today. Bye-bye. See you next time.